flyback converter is probably the most versatile and effective power supply in all of power electronics. It is able to be configured as either a step up or a step down converter, which gives it a huge range of applications. It utilizes a special component known as a transformer, which enables it to handle a super wide range of both AC and DC input voltages, as well as provides galvanic isolation to the user, which is a requirement by a lot of electrical safety standards. In this video, we are going to do a full detailed breakdown of the flyback converter. We are going to analyze its key components, theory of operations, and any other important concepts that you need to know in order to understand how this topology works. The main goal with this video is to just give you an introduction to the flyback converter and establish a solid foundation before we start doing some actual design work. Also, there will be a bunch of free resources that you might find helpful, so feel free to check those out as well. And with that, let's get right into it. So the first thing we want to do is open up TI's Power Topologies Handbook and navigate to the flyback converters section. Here, we will find a circuit diagram that shows what is referred to as the power stage of the flyback converter, which is essentially all of the components that do the heavy lifting and the work in order to convert one voltage to another voltage. The first component we're going to talk about is CI, the input capacitor. With flyback converters, you'll often hear the term input capacitor or bulk capacitor, or a combination of the two, but its function in every case is the same. Just like with other power supplies, the job of the input capacitor on the flyback converter is to smooth out the input voltage and provide a clean, stable signal for the flyback converter to work with. While it is very similar to the input capacitors of other converters like the buck and boost converter, there are some key differences that I want to talk about. One is the input voltage rating. See, flyback converters are usually designed for offline applications, meaning they receive their input voltage directly from the AC mains, aka like your wall outlet. That means your input capacitor's voltage rating is going to be substantially higher than with other typical applications. Another point on that note is that the rectified AC mains voltage source will have these huge peaks and valleys that the capacitor has to smooth out. So oftentimes their capacitance ratings are substantially higher than that of the buck and boost converter applications that we've talked about. When it comes to selecting an input capacitor for a flyback converter applications, you'll want to be familiar with parameters such as voltage rating, capacitance value, ripple current rating, lead spacing is something to consider, and standoff height. The most common material type you'll see for these types of capacitors is going to be aluminum electrolytic, because they are what can offer your really high voltage ratings as well as your really high capacitance values. One important thing to note about aluminum electrolytic capacitors is that they're actually polarized, meaning they have a positive and negative terminal which need to be wired properly in order to work. The next component we will talk about is going to be the transformer, which is what this symbol on the schematic represents. I definitely remember having a hard time understanding the transformer whenever I was first starting out. And the reason for that is because there's actually quite a lot going on with this component that's kind of going on behind the scenes or under the hood. So you kind of have to do some digging in order to understand how it truly operates. So to try to give you the best understanding of how this component works, I'm going to explain it from like two different perspectives. One is going to be the physics perspective. So physically, I think the best way to view the transformer is to view it like a pair of electromagnets that have been placed within each other's magnetic field. One of the magnets is referred to as the primary side of the transformer, and the other magnet is referred to as the secondary side of the transformer. Now, it's important to note, and this kind of blew my mind when I learned this, these two electromagnets are not electrically connected to each other. Instead, they use their magnetic fields to sort of communicate with one another like wirelessly. In physics, there is a phenomenon known as Faraday's law, which kind of describes this whole process. I'm not going to go into that in too much detail in this video, so instead I'll drop a link in the description for a more detailed video on Faraday's law. But for right now, we'll just talk about two of the key concepts from Faraday's law that I think you should understand if you want to understand how a transformer works. Number one is that any wire that is carrying current will generate a magnetic field. Number two is that a closed circuit that is experiencing a changing magnetic field will have a voltage induced upon it. The transformer uses both of these principles in order to operate and allow the primary side to transfer power to the secondary side. That's how you get your output. Okay, so now we'll talk about the second perspective to understand transformers, and that's going to be looking at it like an electronic component. Electrically, we can look at the transformer like a pair of inductors who are linked or coupled together, meaning that what happens to one of the inductors, you'll have an equivalent reaction in the other inductor. So let's think of an example real quick. So let's say I am driving current through one of the inductors. Then as a result, the second inductor, the other inductor, will want to have current flowing through it as well. So you'll have a relationship there between your primary side inductor and your secondary side inductor. So by controlling the current through the primary side, you can effectively control current through the secondary side. And on this topic, one thing I want to note is you'll oftentimes actually see dots on the transformer, and this is to denote the relationship in the direction of the currents flowing in the transformer. I like to think of it sort of like that video game Portal, where if you have current flowing into one of the dots, you'll want to have current flowing out of the other dot. So we'll talk more about the transformer's behavior when we get to the theory of operations sections, but I think that's a good enough explanation for how it works for right now. So let's go ahead and cover some of the important parameters of the transformer that you should be familiar with when you're working and designing with this component. The first one is going to be your transformer's winding ratio. This is a ratio of the number of windings in the primary, meaning the number of times the copper wire is wound around your magnetic or iron core, and the ratio of that to the secondary winding. So how many times the secondary winding is wound around the core. There's going to be a ratio between those two, and that helps determine the output voltage that you see on the secondary side, or at least the relationship between your input and your output voltage. This is one of the reasons why the transformer can be configured as either a step up or a step down converter, because you can have a winding ratio where you have more windings on your secondary, you can have less windings on your secondary, or you can have the same number of windings on your secondary. So it gives you a lot of flexibility with your design choices there. Another important parameter you should be familiar with is the inductance. So just like an inductor, the transformer will have an inductance. More specifically, it's the primary side inductance that you should be familiar with. And in terms of the transformer, think of the inductance value as how strong of a magnetic field the winding can generate. Then you have other typical parameters such as current rating, which is just how much current you can drive through your transformer. Saturation current rating is also important because we're kind of looking at it like an inductor. And then there's another key parameter known as isolation rating, which is just a measure of how insulated the transformer's windings are from each other electrically. So a lot of times, if you open up the inside of a transformer, you'll see some insulative tape wrapped around the transformer. And this is what is used to create the galvanic isolation between the primary and the secondary, so that they're not electrically touching, they're transmitting power wirelessly. One important thing to note for flyback transformers is that their design is oftentimes custom. So what you'll typically do is you'll spec out all the parameters we just talked about, and you'll send those to a transformer manufacturer, for example, like Coilcraft, or Mentronics is a big one, Pactra I know is a big one, and they will help you to manufacture your transformer, and that's typically how the process is done. Okay, so next up we have the MOSFET. And like with other switch mode power supplies, it is the job of the MOSFET to act as a switch that controls current through the inductor, and in this case it's going to be the primary side of our transformer. Like with the boost converter, the source pin of the MOSFET is connected to ground, so whenever the switch is on, you create a very low impedance pathway to ground for the current through the transformer to ramp up. However, it also acts a bit like the MOSFET in the buck converter, because when the MOSFET is turned off, no current flows through the primary side winding. The key parameters you need to be familiar with when selecting a MOSFET for your flyback converter application are going to be things like your drain to source voltage rating, your current rating, your power dissipation rating, and the thermal characteristics of the MOSFET. Note that just like with our input capacitor, you'll usually see some pretty high voltage ratings on your MOSFET because their input voltage is so high. So it's not uncommon to see MOSFETs rated at 600, 650 volts. And we'll talk more about why that is the case later. Alrighty, so the next component on the list is going to be the rectifier diode. And the purpose of this component is to only allow current to flow in one direction on the secondary side of the transformer. Now, it may not be super clear why we even need this component to begin with, but when we go over the theory of operations of the flyback converter, we'll understand why it's essential. When selecting a rectifier diode for a flyback converter application, you'll want to be familiar with parameters like your reverse breakdown voltage, your current rating, your power dissipation rating, and your thermal performance. All right, so the last component on our list is going to be the output capacitor. And just like with the buck and boost converter, it is the job of the output capacitor to smooth out the DC voltage ripple that is generated by the switching of the MOSFET. One key difference though is, and you'll find this with all switch mode power supplies generally, is that the envelope or the waveform of the output voltage and output current signal, they don't all look the same depending on your topology. So that's going to impact things like your ripple current rating and your capacitance value for your capacitor. Here are the ones that you want to be familiar with when selecting this part. So you have, of course, your voltage rating, your capacitance rating, your equivalent series resistance, and your ripple current rating. Typically, you'll find aluminum polymer capacitors used for output capacitors on flyback converter applications. And the reason being, it's the same reason as the input capacitor is, that's the material that can usually offer the high capacitance values you need, the high ripple current ratings you need at the high switching frequencies. Oh, and before we go on to the theory of operations section, there's another component that I want to mention that is not shown on the power stage for the flyback converter, and that is going to be your full wave bridge rectifier. And that component goes before your input capacitor, and its job is to rectify your AC input signal into a DC signal. So whenever you're selecting the component or components for your input bridge rectifier, you want to be familiar with parameters such as your reverse breakdown voltage, your current rating, power dissipation rating, and the thermal characteristics. The reason why I say component or components is because oftentimes you can see an input bridge rectifier manufacturers will make them as a package. So instead of having to pick 4 separate diodes out and wire them up yourself, you'll have a package that has already wired them up for you internally. And so you just have, you have to hook up your AC mains, and then you have your positive and negative terminals, and that's all you have to wire. But their parameters will still be the same. So now that we have talked about all of the components that make up the flyback converter circuit, we're going to go ahead and talk about the modes of operation of the flyback converter. So the best way to understand how a flyback converter works is to look at it during 2 conditions. One is when the MOSFET is on, the other is when the MOSFET is off. So when the MOSFET is on, the primary side of the transformer essentially becomes shorted to ground. Because we can look at the primary side of the transformer as an inductor, we know that it will resist any changes to the amount of current flowing through it. So what will happen is the current through the transformer will start to gradually ramp up in a linear fashion, increasing over time. The current through the transformer will generate a magnetic field, so as the amount of current through the transformer increases, so will the strength of the magnetic field. And because the secondary side of the transformer is experiencing a changing magnetic field, we will have a voltage induced in the secondary winding. Now, if you remember in the previous section how we talked about the dots on the transformer denote the relationship between the current flowing into and out of the transformer. So in this example, if the current is flowing into the dot on the primary side, it will want to be flowing out of the dot on the secondary side. So in this case, flowing out of the dot on the secondary side means we'll be flowing against the direction of the diode. So as a result, no current actually flows in the output while the MOSFET is on. Instead, what happens is our magnetic field continues to grow as current through the primary side ramps up, and energy gets stored in the magnetic field of the transformer. This phase is commonly referred to as the energy storage phase of the flyback converter's operation, and it's because of what we just discussed, where energy is being stored in the magnetic field of our transformer. This is similar to the charging phase of the buck and boost converter circuits. The next phase is when the MOSFET is turned off. So when the MOSFET gets turned off, the current through the primary side will abruptly halt. And as a result, the magnetic field being generated by the primary side of the transformer immediately collapses. And this change in magnetic field will also induce a voltage in our primary side. So think about it how we had a growing magnetic field when the FET was on, and in this case we have a shrinking magnetic field, and it's just a very rapidly shrinking one. However, because the direction of the change in the magnetic field is opposite in this case, again, we're going from a growing magnetic field to a shrinking magnetic field, the polarity of the voltage induced in the output will be opposite now. So current will try to flow the other way through the secondary winding. So the rectifier diode will now be forward biased and current will be able to flow on the secondary side. This phase of operation is known as the energy transfer phase because the energy that was previously being stored in the primary winding's magnetic field gets transferred over to the secondary winding. One important concept I want to talk about during the energy transfer phase of the flyback converter's operation is something that is referred to as the reflected output voltage. This is an additional voltage that is reflected back onto the primary winding when current is flowing through the secondary side of the transformer. There are sort of two ways to explain why this happens. The first way is whenever we think about the primary side of the transformer as an inductor, and we know that inductors like to resist any changes in the amount of current flowing through them. So when we abruptly open the switch when the MOSFET turns off, there's nowhere for current to go. And so what's going to happen is your primary side of your transformer, that inductor will try to raise its voltage to keep pushing current through that MOSFET. And so as a result, you get a huge voltage spike. The other way to think about it is, as we mentioned, the inductors, the primary and secondary side, are coupled. And so whenever you have current flowing through one of them, you'll have an equivalent reaction in the other one. So in the energy transfer phase, we have current flowing through our secondary winding. So as a result, current will want to also flow through the primary winding. So that's kind of two ways to conceptualize what the reflected output voltage is. Where it kind of comes into play when you're designing your circuit is that it's an additional voltage stress that your MOSFET will see, so you have to design your MOSFET for it. So that's actually why you see MOSFETs rated for 650 volts or higher. Now I understand that that was a lot of information to digest and comprehend, so I want to review some of the important details and go over some things to help cement your understanding of the flyback converter. So a lot of the details have to do with the operation of the transformer and the process by which a voltage gets induced into the secondary winding. Step one is to generate a changing current, right? The way we get a changing current is we have current that has been ramping up in the primary side this whole time while the MOSFET's on, and then when the MOSFET is turned off, that abruptly changes the current, right? You get current flowing from some positive value down to zero, right? That's a change in current flowing through the transformer. And Faraday's law states that this change in current will also result in a change in magnetic field. In other words, we had a magnetic field that was being generated by the current flowing through the transformer, and now we don't because there's no more current flowing through the transformer. And remember, the second point of Faraday's law is that a changing magnetic field will induce a voltage in a nearby circuit. And in this case, it's the secondary winding of the transformer. So that's how we end up with a voltage being induced on our secondary side. And one last important observation I want to make is about the current waveforms in the transformer. If you go on the VI's Power Topologies Handbook, you'll see these wonderful graphs that show current through the primary and secondary winding, right? So you can see the current ramping up in the primary side, and in the secondary side, what it looks like is it actually is ramping down during the energy transfer phase, right? AKA the discharging phase, if you want to think about it in terms of the buck or boost converter. So what's interesting in this case is that if you place those primary and secondary side current waveforms right next to each other, it looks like a normal, buck or boost converter's inductor current waveform, right? Where you have the triangular looking wave, the current ramping up, current ramping down. So the interesting observation about that is we're actually only using half of that waveform, right? Because the current flowing through our load is only the current flowing in the secondary side. So you're basically only getting half of that triangle looking waveform. And as a result, what happens is you just have to generate higher peak currents in order to get your average current on the secondary side to be adequate per your power supply specifications. But I thought that was just an interesting observation to make, try to really bridge the gap and understand that it's kind of just like inductors that we're dealing with still. Okay, to wrap things up, I want to go over some frequently asked questions that people usually have when they are learning about the flyback converter. So the first question is going to be, what happens if the MOSFET stays on forever? So just like in the example with the boost converter, if the MOSFET stays on forever, then current through the primary side of the transformer will continue to ramp up indefinitely. However, because the diode will remain reverse biased, nothing will actually happen in the output. Then the next question is, what happens if the MOSFET stays off forever? So if the MOSFET stays off forever, what will happen is no current will flow through the primary winding, and therefore you will get no magnetic field generated, and so you won't see any voltage on the secondary side of the output at all, and so again, nothing will happen. This is actually kind of the magic behind the flyback converter though, is it requires both the switching on and off of the MOSFET in order to generate an output voltage. So it actually makes it very safe, because in either event of a malfunctioning MOSFET, you're never going to get a voltage on your output, which makes it extremely safe for the user. So I hope all of that made sense to you. If you have any questions, feel free to drop them in the comments below. I respond to every single comment on here. Thank you so much if you made it to the end of the video, and hopefully I will see you in the next one.